observation, at least to make one comment about it. If in the standard method, if you treat benzene with an acid chloride and aluminium trichloride, what you get is that. And if you carry out then a let's see what we have here. Audio. Boom, 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 boom. Okay, if you then treat that with zinc and concentrated HCl, what happens is that the carbonyl oxygen is replaced by two hydrogens. So as a result of carrying out those two steps, what you achieve is an alkylation of benzene. And unlike the Friedel-Crafts alkylation, this route does not result in polysubstitution. The reason being that the initial Friedel-Crafts acylation product is less reactive than benzene, so the reaction stops there. You can also do this reaction in an intramolecular way. If you, for example, use that anhydride, what you will get is that material, and this of course has an acyl group on benzene, but it's a somewhat more complicated acyl group because instead of just having a carbon chain like here, which could be methyl, ethyl, propyl, butyl, and so on, this has got a carbon chain ending in some sort of functional group, in fact, in a carboxylic acid. And now, if you do the zinc HCl business on it, in other words, the Clemmensen reduction, you will remove the carbonyl group. So now, you have a benzene ring attached to a carbon chain ending in a carboxyl group. And if you convert that carboxyl group into an acid chloride, which is done very often with thionyl chloride, you now come to a substance that can do an intramolecular Friedel-Crafts acylation. So you end up with a cyclic ketone. So the point that I'm trying to make is that you can carry out Friedel-Crafts acylations in an intermolecular manner, in other words, between two different molecules, or you can have the acylating unit at the end of a chain that's already attached to the benzene ring. When you do that, you make a new ring, as I've got here. And this substance is a substance called ketone, and Dr. Haley Wan, who's in charge of the undergraduate labs, tells me that next week you're going to do something called a Grignard reaction in the lab. So I might just spend one moment just giving you a very, very brief intro to the Grignard reaction. If you take any alkyl halide, it's frequently an iodide or a bromide, and you treat it with magnesium in ether, what you get is a substance that behaves as though it is that. And this substance, I'll use that very same ketone. That substance will react in the way that I'm showing to give you first a salt, it'll be a magnesium salt. And if you pour that into water, you will get what's called a tertiary alcohol. So she didn't tell me exactly what experiment you're going to be doing, but she said you're going to be doing a Grignard reaction, and this is a standard Grignard reaction named after the very famous French chemist and Nobel Prize winner, Victor Grignard. There's a famous photograph of Grignard giving a lecture. This is stuff written on the blackboard, except there's a mistake. He made a mistake or something. Big mistake on the blackboard. Okay, I've done enough. I've told you enough about the three-part acylation. I've indicated to you you can do it intermolecularly and intramolecularly, and I've also made it clear that it's very often used in combination with what's called the Clemmensen reduction, which replaces the original carbonyl group by two hydrogens attached to carbon. Now what I want to do is to give you an explanation for things that I told you in the last lecture. Because in the last lecture I said, if you've got a substituent on a benzene ring, and then you carry out another electrophilic aromatic substitution, you will find two things. Sometimes, depending on the substituent, the next electrophilic aromatic substitution will be easier than it was for benzene, and sometimes it will be harder. It's either faster or slower. And we say that the substituents, if the next step is faster, we call them activating substituents. And if the next step is slower, we call them deactivating substituents. All that makes sense. You don't have to know any chemistry. You just have to know some English. The other thing that you'll find is that once you've got a substituent present, the next electrophilic aromatic substitution places the substituent in certain positions. Not in any old position, but in certain positions. And it turns out that there are two types of result. One is that the positions in which the second substituent are placed are ortho and para to the first substituent. And the other result is that the second substituent goes into meta. So it's either ortho and para or meta, not both. And I gave you a list of groups that are activating and ortho-para directing. I then gave you a very small list of groups, mainly the halogens and CH2Cl, that are ortho-para directing and deactivating. And then I gave you a larger list of groups that are deactivating and meta-directing. And I just told you that's the way it is. You don't like it? Go to another planet where the rules are different. That's the way it is here. What I want to do now is to explain to you why this result is observed. It's very easy to understand once you've been shown. What I will do first is, let's see what the book does first. No, I don't care what the book does first. I'll tell you the way I like it. I will put a simple alkyl group on the benzene ring. The simplest alkyl group is the methyl group. And now I want to explain two things. Why is the alkyl group activating? And why is it that the next electrophilic aromatic substitution will go into the ortho and the para positions? Now why it's activating is very easy to understand, because you know from last term's chemistry that if you have a secondary carbocation, it is more stable and a primary carbocation. And the reason that was given to you is that alkyl groups are electron pushing groups. Probably a very good reason why that electron pushing groups wasn't given. We won't worry about that. You have to take it as the gospel truth that they are electron pushing groups. So if you've got an electron pushing group, such as an alkyl group, for example, the simplest one, methyl, but it applies to ethyl, propyl, butyl, cyclohexyl, whatever you like. If you've got an electron pushing group, pushing electron density into the ring, then you know that it's more likely that the ring would be willing to donate some electron density to an electrophile. You know, if you're very poor and you're asked for a charitable donation, you can give $5. But if you're Bill Gates, you can give $5 million. You've got more money, you can give more. It's easier for you. Giving $5 million is about the same as one of us giving 25 cents, I guess. So if this benzene ring has an electron pushing group on it, it's more willing to give electron density to the electrophile. And you remember I used this childish word in telling you the other day that electrons leak out onto the electrophile. And so it's very easy to understand that this is activated. But what's not so easy to understand until it's explained to you is, why does the electrophile go in the ortho and para positions? And the way to understand that is very easy. You first play dumb. You pretend you don't know where the electrophile is going to go. Now, there are only 3 places. There are 2 ortho positions to the methyl group. They're the same by symmetry. There are 2 meta positions to the methyl group. They're the same by symmetry. And there's 1 para position. So there are 3 positions. Here, you don't have to worry about that because it's the same as that. Here, you don't have to worry about that because it's the same as this. That's the second position, that's the third. So you pretend you don't know. And you write down the intermediates that are appropriate for attack at the ortho position. And then you write down the intermediates that are appropriate for attack at the para position. And then you write down the intermediates that are appropriate for attack at the meta position. And if you do that, you will notice something. You will notice that the intermediates for the ortho and para attack, there's something about them that makes them more favorable than the intermediate for meta attack. And once you know that the ortho-para is more favorable than meta, of course you've answered the question, why does it go ortho-para? So let's do that. Let us pretend we don't know, and I'm going to write, let's say, let me do the para one first. So I've got some intermediate, I'll call it E+. No, I don't want to do that. Just hang on a moment. So that is one of the species that would be formed if the electrophile attacks in the para position. And I'm going to write down another resonance structure for this. I'm going to move the arrows like that. And then I'm going to write down yet another resonance structure. Then put a little methyl group to show you that the methyl group is pushing electron density towards that carbocation. So there are, oops, I better emboss the methyl group, we don't want to do that. So I've got the resonance structures. Now I want to do the same thing for ortho attack. Resonance structures. I'll move the double bond. It's not really a double bond, but we draw it to look like one. And then I'm going to draw another resonance structure. So there I've got the resonance structures. Now I've written down what I anticipate will be the intermediate species for attack at the para position to the methyl substituent, and I've written down what I anticipate will be the intermediate species for attack at the ortho position. And now I'm going to write down the intermediate species that I anticipate would be formed if the attack occurs at the meta position. Let me do the meta at the bottom here, and let's see if I can't get a different coloured pen. It'll have to be in red. So I'm going to put here now what I expect for meta attack. I did that, okay. Let me do one more. So now I've got the resonance structures that would arise if attack occurred in the meta position. So what I've done so far is I've written down all resonance structures that correspond in the first case to para attack, in the second case to ortho attack, and in the third case to meta attack. And I told you 5 minutes ago that if you go through this exercise and write down the various structures, the resonance structures for the intermediates formed for each of these methods of attack, you would find that for the ortho-para, which is the experimental result, you would notice that there was something very favorable about the resonance structures. And just before telling you that, I reminded you that a primary carbocation is less stable than a secondary, which is less stable than a tertiary. So if you have an electron pushing group, an alkyl group, say, on a carbon that has a positive charge, that is more favorable than if you don't have a carbon pushing to that positively charged carbon. Now, if you look at the case for para, we've got 1, 2, 3 resonance structures. You look at the case for ortho, 1, 2, 3. You look at the case for meta, you've got 3. So in every case, you've got 3 resonance structures. But if you examine the resonance structures for para attack, you will see that one of the structures is especially favorable because it has on its positively charged carbon an electron pushing group, and that should remind you of everything I said with respect to those carbocations. And if you look at the resonance structures for ortho attack, again you will see one of them has a positively charged carbon carrying an electron pushing group, which is good news. But if you look at the resonance structures for meta attack, there is no such favorable carbocation. And so it's easy to understand why, of the 3 possibilities, meta attack is the least favorable. And if meta attack is the least favorable, it means that ortho and para are the most favorable, which means, of course, that if you do the experiment, you're going to get ortho and para substitution. So that's the explanation for this, where you have an alkyl group. But an alkyl group is not the only group that activates the ring by pushing electron density towards it, and that directs ortho-para. The majority of the groups that do that, as you should remember, are groups that have a heteroatom joined to the benzene ring, like an OH, an OMe, NH2, and so forth and so on. So what I want to do now is to explain to you why and how it is that those groups activate the ring and direct ortho-para. And the procedure that I'll use is to first play dumb, pretend I don't know, write down all the possibilities, and I should then see that for ortho and para substitution, that there's something about the resonance structures that makes them more favorable than the resonance structures for meta substitution. And it would be a bit more complicated than this, because in this case, in every example, there was the same number of resonance structures. When you have a heteroatom, it's not the same number of resonance structures. So I will clean the board and I'll then go through the exercise for these other possibilities. Now, just to remind you, I've used a simple E to represent the electrophile. It can be nitronium ion, it can be SO3, it can be a acylium ion, it can be a carbocation, it could be a bromine, complex to ferric chloride. Everything I've said for this hypothetical electrophile E applies to all of them. Okay, so let me work out for you what happens if you have a substituent that's a heteroatom. So that's the situation. Now, you know that oxygen is electronegative. Therefore, that oxygen is sucking electron density out of the ring. That should tell you that the ring is deactivated. But in fact, the experiment shows that the ring is activated. So there's something else going on. And the something else that's going on is due to the presence of the lone pairs on the oxygen. And as you will see, the lone pairs on the oxygen, at least one of them, can feed into the benzene ring. If it feeds into the benzene ring, it makes the ring activated. So you've got two effects. The electron withdrawing effect due to the electronegativity, which deactivates the ring, and what's called the conjugation effect due to the lone pair on the oxygen, which activates the ring. It turns out that the activation is bigger than the deactivation, so overall the ring is activated and actually strongly activated. So that's the explanation of why this stuff, and something with an OH instead of an OMe, or an NH2, or an O-acetyl, yes sir. Okay, the fact that this is electronegative and is sucking electron density out of the ring is, the word for it is induction. It withdraws electron density by induction. So, let's work out why this group is autocalor-directing, and at the same time you'll get some more information as to why it's activating. And we're going to do it by writing down various structures for the intermediates formed by auto-attack. We'll do it again for para-attack, and we'll do it again for meta-attack, and you'll see that the autocalor are favoured over meta. So let me start again with para as before. And so what I will do, I will bring electrons out in the para position. I will write yet another resonance structure. Write again a resonance structure. And I will write that fourth resonance structure. And you can see that in that resonance structure, electrons from the oxygen have been fed into the ring. And since electrons are fed into the ring, provided that that effect is stronger than the inductive withdrawal of electron density along this bond because of the electronegativity of oxygen, provided that resonance effect is bigger, then the ring will be activated. Then it is bigger. Now let's see what happens if we carry out the electrophilic aromatic substitution in the ortho position. And once again, I will write an additional resonance structure in which electrons are fed towards, well, actually into the ring. Oops, we don't want that. So again, you have an additional resonance structure made possible by the fact that the lone pair of electrons on the heteroatom, in this case oxygen, can be donated towards the ring. So instead of the ring bearing a positive charge, the ring is neutral, and the heteroatom bears a positive charge. And that effect is stronger than the inductive electron withdrawing effect of the oxygen that's due to its electronegativity. So now what I've got to do is to go through the same exercise for meta-attack. Now, if I write on that board, you can't see it. If I write on that board, you guys can't see it. You can all see that there are 4 resonance structures for ortho-attack. There are 4 resonance structures for para-attack. And so I'm going to rub out this one, and over here I'm going to write the meta, the results for the meta. Yeah, that's not good. So I got 1, 2, 3. That's all there is. You see, I cannot write a resonance structure invoking or using the electron pair on the oxygen so as to quench the positive charge that's on the ring. So you can see something now. You can see that for ortho and para attack, there are more resonance structures than for meta attack. And you remember that the other day I gave you a bunch of little rules for writing resonance structures, and I said the more resonance structures you can write, the more stable the species is. And so it's clear now why, when you have a methoxy group, or some group with a lone pair of electrons, that the intermediate form for ortho-attack and for para-attack, those intermediates are more stable than the intermediate form for meta-attack. And so that tells you why those groups are ortho-para-directing groups. And the only thing that you have to take on a bit of faith is the fact that the resonance effect which brings this lone pair towards the ring, that overwhelms the electron withdrawing inductive effect due to the electronegativity of the oxygen. So now you know why some groups, alkyl groups and groups with heteroatoms, are ortho-para-directing, simply because the intermediates produced, or the intermediates resonance stabilized, so it's a single entity. I've just written down the various resonance forms. The intermediate produced, if attack occurs ortho and para, is more stable than the intermediate produced if the attack goes meta. So now what remains is for me to explain to you why it is that some groups are meta-directing and deactivating. And that's a little more complicated. So I will clean the board and then I will explain to you what the story is for meta-directing groups. I realised that I just told you that I'm going to do something which I actually don't want to do. I said I was going to explain to you why certain groups are meta-directing. Before I do that, I want to deal with the case of the chlorine and bromine and iodine and chlorine, which are deactivating and ortho-para-directing. It's quite easy to deal with that. Okay, so the pictures that I've drawn up are exactly the same as I drew up for the methoxy groups, and I've drawn it up for para attack, and you can see that for para attack you can invoke the lone pair of electrons on the chlorine so that you've got an additional resonance structure. And of course, as you realise, if you write down the corresponding resonance structures for ortho attack, you get exactly the same situation. And you also realise, because it's the same as with methoxy, that if I write down the intermediates for meta attack, I won't be able to write down this extra resonance structure. Now, chlorine is ortho-para-directing and deactivating. And you remember that a moment ago I said that what you had to take as a matter of faith was the fact that the conjugation effect of oxygen, feeding of the oxygen lone pair towards the ring, overwhelmed the inductive electron withdrawing effect due to the electronegativity of oxygen. And that's true, because if you accept that, you understand everything. In the case of chlorine, it turns out that this ability to do this is not strong enough to overcome the electron withdrawing, deactivating effect of the chlorine. So overall, With chlorine there, because the balance of its ability to feed electron density towards the ring versus its inductive electron withdrawing effect is different from oxygen. And the conjugation effect of the chlorine does not overwhelm the inductive electron withdrawing effect of the chlorine. So the chlorine deactivates the ring. But the ability, modest though it is, of chlorine to feed electrons into here makes the resonance structures for ortho attack and for para attack, it gives you an additional resonance structure. It makes it more stable than in the case of meta attack. So that's why chlorine is ortho para directing, even though it's slightly deactivating. That's the explanation for chlorine. Now what we have to do is to explain why the normal meta-directing deactivating groups behave the way that they do. And I will do it in exactly the same way. I'll pretend not to know. I'll write down all the possibilities, and you will see that meta-attack in this case is favoured compared with ortho and para-attack.
Kyle is the shortest.
I'm so scared she's the shortest because that's such a cool project.
What time do you have to start?
Right after this. And psychology afterwards. Which sucks because we're going to send the whole father.
I hate it when you have to start a new paper. Especially in the last 5.
The meta-directing ones are all deactivated.
Yeah.
Okay.
Is there one yesterday? Yeah, the class is pretty full actually. So I don't know about today. It was like 3/4 last quarter. I feel so like busy after because I'm like up a bit.
So that's the situation for ortho attack. Now let me do it for para. And finally, I will do it for Petter.
I just started a para.
Oops, that's no good. And I don't like the green, you probably can't see it. Yeah. There it is. So those are the resonance structures for meta attack. Now, so far, every time I've gone through this exercise, I've drawn the resonance structures for the species for attack at the ortho position. I've repeated that for the species for attack at the para position, and I've repeated it once more for the species formed by attack at the meta position. And so far, in all those cases, there was something especially favorable for the species that resulted from ortho and para attack. This time, there is something especially unfavorable for the species that results from attack at the ortho and para positions. And that feature is that you have a plus charge on a group carrying a positively charged atom. So this is bad. And here you have the same thing. This situation is bad. But for attack at the meta position, you don't have that. And so, although the nitro group withdraws electron density from the ring, and it's very easy to see that it does draw electron density from the ring, because if I write this, I can write another resonance structure in which there's a plus charge on the ring. So clearly the nitro group is going to deactivate the ring. But if I examine the species that are formed for meta attack and for ortho attack and for para attack, I find that in the ortho and para cases, there's something especially unfavorable, and the especially unfavorable feature is that you get a key atom bearing a positive charge on a carbon bearing a positive charge. Whereas for meta attack, you don't get that. So although all the positions on the benzene ring are deactivated, if the electrophile comes in the meta position, that's the least unfavorable. If it goes into the ortho position, it's more unfavorable, and if it goes into the para position, it's also more unfavorable. And so by default, the meta position is the one that is now substituted. And you can write similar arguments for all of the other electron withdrawing meta-directing groups. Okay, somebody asked me what time the Super TA session is tonight in this room. It's 5:15.